I don't know how this long will last because I just charged it for 1 minute. So if you cannot hear me, you can move to the front if the mic stops working. Huh? Somebody did not push it back for charging after the last lecture. Okay, I just want to remind you that midterm exam will be coming up after the break. And you can go to chapter 1 for the requirements and so on. Okay? No need to email me to ask me anything more, because whatever I want to say, it's all there. Alright? Now, well, what have we done so far in the first half of the semester? Well, we have done actually quite a lot. You might think it's just chapter 2 and chapter 3, but chapter 3 is a very long chapter. It's the foundation chapter. So today we are going to complete chapter 3. In fact, we are going to talk about multicollinearity. And this multicollinearity, I call it the curse of linear regression. If you don't deal with it properly, it will come back to haunt you. So it's very important, this multicollinearity. So there's a chapter on it. So after the break next week, we will have 7 weeks left. And if your mathematics is good, you can see that we have chapter 4, 5, 6, 7, 8, 9, 10. 7 chapters, just nice for 7 weeks. So approximately, we are going to do a chapter every week after the break. Honeymoon is over, okay? Well, some of these chapters are quite short, some are a little bit longer, but according to my experience last semester, I'm sure I can complete it. So there's no worry. In fact, this semester, I've slowed down. Last semester, I covered all the way up to chapter 4. But I decided to do it slowly so that you can understand chapter 3 thoroughly. So after chapter 3, we are going to look at 4, 5, 6 additional topics that will be applied to multiple linear regression. After that, we look at 2 special types of multiple linear regression models here that are commonly in use. I hope you can quiet down when I talk. I appreciate that. So these 2 are special cases of multiple linear regression, and they are very common, very useful. So we have 2 separate chapters on it, and then we talk about multicollinearity, and finally variable selection. So if you have, if you start with 50 variables, how do you select the more useful one and delete the not so useful one? So that's the plan. So I'm going to talk about this multicollinearity. As I told you, we are going to do an in-depth study of multicollinearity in chapter 9, which is the most theoretical chapter in this course. And there are some very advanced concepts and ideas in chapter 9. So here, I'm just going to give you an introduction to it. To understand roughly what is multicollinearity. Okay? And what is the effect of multicollinearity? Alright. So we will take a look at pages 3 to 6 for multicollinearity. And then the second topic is, why do some regression coefficients have the wrong sign? You know that if you increase x1, a particular regressive variable, y will go up, the response. But somehow the regression coefficient is not positive, it's negative. So how can that happen? Yeah. I will explain it. There are a few reasons for it. And then X matrix with orthogonal columns. Now this is a very important topic in design of experiments, which many of you will probably take it after this module. And so I will explain what is orthogonal later. All right. So let's start with a very simple definition for multicollinearity. Well, what is multicollinearity? Well, it's just dependence, very strong dependence among the regressive variables. So if you have two variables that are highly correlated, then that's called multicollinearity. For example, if you look at the car data that we have been analyzing, the engine capacity and the weight, they are all highly correlated. The weight and the length, for example, they are highly correlated. If you look at PR2103 data, the student data that I collected, some variables are highly correlated. For example, the weight and height, I think they are also quite highly correlated. So now let's look at an example here. Look at the delivery time data, and we talk about standardizing the regressive variables. There are two ways to standardize regressive variables. One is scale to unit normal. One is scale to unit length. And I believe I told you, scale to unit length, it's the more useful one. Because if you scale the variables, the regressive variables to unit length, your x prime x matrix, which I call w prime w now, based on the scale variables, is actually the variance covariance matrix. So this w prime w is the variance covariance matrix of the scale regressive variables. So 0.824, that is the correlation between regressor 1 and regressor 2. There are only two regressors there. One is the number of cases, one is the distance. So this 0.824212, 0.824215 is the correlation between the distance and the case. After they have been, it's a correlation. And if you scale them, your x prime x matrix based on the scale variable will be this. And W prime W inverse is over there. Alright? So now what is the variance? So I am going to I'm just going to show you the formula beta naught, beta 1 is sigma square W prime W inverse. Remember, I'm now talking about scale variables. So the case and distance have been scaled, and the variance, the variance of beta naught and beta 1 is given by this quantity. I think I need this variance of this. Let me just check. I think it's fine. Variance of beta n. Okay. So what does that mean? So what happened here is you have sigma squared and 3.11 minus 2.57. Let me just take the first two decimal place. So this variance of beta naught hat will be sigma squared times 3.11. Variance of beta 1 hat is sigma squared 3.11. In fact, they're the same variance. Alright? So you bring the sigma square over, you have 3.11. 841. So in terms of so the variance of beta naught is sigma squared multiplied by this factor, yeah, multiplied by a factor of 3.11, and this factor it's called variance inflation factor. Variance inflation factor. So it's 3.11 sigma squared. Alright? Now, well, we cannot say that this variance is big or small unless we compare with some other examples. So let's look at another case where there is independence among the regressor variables. So here, I can choose a hypothetical data where the correlation between the two regressor variables is 0. Now the data is here. You can choose. There are so many. There's an infinite number of data you can choose that will have this special W prime W matrix. So for this data set, there are 2 points at each of this location. So there are 8 points altogether. And if you calculate the correlation coefficient between x1 and x2, it will be 0. Alright? So the covariance is 0, put it this way. There's no linear relationship, in other words. And W prime W, in this case, it's the identity matrix. So what is the variance of beta 1 and beta 2? Sorry, they use beta 1 and 2. I should be using because after I scale it to unit length, this beta 0 is gone, is 0. Yeah? We can prove it in a tutorial that's coming up. So we only have beta 1 and beta 2. Doesn't matter whether I use beta B1 is the same. Alright, so for this case, you can see that, okay, I'm going to maybe I will stick to the notation used, not confuse you. Okay, B1, B2, and here I'm going to change it also. B1, B2, B2. Okay, so here, for this case, our variance of B1 is sigma squared times 1. Variance of B2 is sigma squared times 1. So what is the variance inflation factor? The variance inflation factor is 1. Right? Is here. The diagonal elements are called the variance inflation factor. So these two examples tell us one thing. For the case where you have near dependence among the regressive variables, the variance inflation factor is larger. If you have independence, that means there is no multi-collinearity, then the variance inflation factor is only 1. So, now the question is, well, why do we care so much about variance inflation factor? Well, we care because we are talking about variance of beta 1 head and variance of beta 2 head. You see, variance is a measure of accuracy. If the variance of beta 1 head is small, that means you are estimating beta 1 accurately. If the variance is large, that means your estimator beta 1 is not so trustworthy. So the smaller the variance, the better. And sometimes, and for this case, you can see, if I have independence among the regressor, between the two regressor variables, I have a small variance. And if I have a near dependency, 0.85 is pretty strong, or 82 is pretty strong, and I have a larger variance. So, this means, so this shows the effect of multi-collinearity on the variance of the estimator. The more correlated they are, the more highly correlated they are, the variance become larger. Sometimes, the correlation can be so high that the variance is so high, it renders it completely useless. So that's the problem with multi-collinearity. So I have conveyed two important points by now. Number one, what is multi-collinearity? Very simple. It's dependency, high dependency among regressive variables. That's called multi-collinearity. So fact number two, what is the effect of multicollinearity? Why do we bother if some regressor variables are correlated? Well, in a way, if you have two regressor variables that are highly correlated, that means they convey the same information. So it does not make sense to have the two of them there. One is enough. If you include both of them, you're going to have trouble. What happened is the variance of your regression coefficient will become very large. The higher the dependency, the higher is the variance. Okay? So that is multicollinearity. Alright. So now we know that x prime x inverse, beta hat it's x prime x inverse x prime y. So x prime x inverse, we know what's the use. It's basically for finding the estimate of the regression coefficient. But now we know that the diagonal elements of this matrix x prime x inverse has certain significance, and those diagonal elements are called variance inflation factors. So you can examine this matrix x prime x inverse. The diagonal element, any diagonal element is large, it means the beta associated with this diagonal element will have a large variance. Okay, so, and these diagonal elements are called variance inflation factor. How much it inflates the variance? Yeah. And here, remember, I have, when we talk about variance inflation factor, we actually scale to unit length first, and then we calculate this x prime x inverse. So this x prime x inverse matrix is actually W prime W inverse. Alright? But I'm writing it as x prime x inverse. So beta naught is not being considered for variance inflation factor. Okay? So here are some facts about x prime x. So here, I'm going to try to explain another time how multicollinearity affects the variance of a regression coefficient. So now let's just suppose all the regressors variables are unit length scale. An interesting thing is, if you have variables already unit length scale and you do again unit length scale, you get the same variable. You can prove it mathematically. Very simple. Now the x prime x matrix is in the correlation form. I've been using W prime W, but now I'm going to use x prime x. Just remember this. This is the important condition. This one. Alright. The variance inflation factor is the J diagonal element for J running from 1 to K. And it can be shown. It may not be easy to show, but it can be shown. So these results actually are quite hard to prove because it's the work of many researchers over the many years. Here we are just looking at some of the results. Now this variance inflation factor, the diagonal element, the J, let's look at the J, is equal to 1 over 1 minus Rj squared. it's 1 over 1 minus Rj squared. And this is the coefficient of determination when xj is regressed with the remaining k minus 1 regressor variable. That means you only focus on the regressor variable. Use xj as the response, and then you regress it against all the other k minus 1 regressor variable. And Rj squared is the R squared statistics that you will get. Remember, R squared is what? R squared measures the dependency of your response with your regressor variable. So if Sj is nearly dependent on some subset of the regressor variable, this one will be near 1. So that means we are now using this R squared as a measure of dependency of one regressor variable, xj, with the rest. We are not even talking about a relationship between two. It could be xj with all the rest at the same time. So Rj squared is a measure of that dependency. If Rj squared is near 1, that means one regressor variable is highly correlated with some subset of the rest of the regressor variable. So this is near 1. Now if this is 1, near 1, what happens? The denominator becomes near 0. If the denominator becomes near 0, this Cjj will explode. 1 divided by a very small number. You are going to get large value. So this is another proof. Basically it's a proof why dependency of xj with the other xj will cause an inflation in the variance of beta j. So if what about if xj is orthogonal? Orthogonal, I'm going to explain a bit later. Orthogonal implies independence. If xj is independent from the remaining variables, then Rj squared that you calculated will be near 0, and then VIF will be near 1, as you can see from the simple example that I gave you earlier. So if all the regressor variables are independent, we are interested in one form of independence called orthogonal, which I will explain later. Then Rj, if they are independent, then this Cjj will be small. So in other words, this one says the VIFJ measures how much the variance of the regression coefficient beta j is affected by the relationship of fj with the other variables. Yeah? So if there's a relationship, VIFJ will be large. If there's no relationship, VIFJ will be small. So we can actually use this to detect multi-collinearity, which we are going to talk more about it later. In fact, how to deal with it. But here's just detection. So if you see any VIF that is at least 2.5, that means, this is a very rough rule of thumb. It's subjective. Then we say there's some evidence of multi-collinearity. Some say, hey, 2.5 is too small, use 5. See, there's some subjectivity. So for me, 2.5 or 5 is fine. If I have to set an exam question, I will give you a VIF like 8. I won't choose 3. 3, then you don't know which one to use, right? So don't worry. Everything will be crystal clear in an exam. So, the next question is, all this, what I talk about, they are all very beautiful, but remain useless unless you know how to find a VIF. In fact, to find a VIF is very simple. You scale the variables to unit length, find x prime x inverse. That's it. Or, in R, there's a very beautiful function. Guess the name. Variable inflation factor. How nice. You just say, you fit a model, and then you say VIF fitted model. It will show you all the variance inflation factors. Yeah. So for, of course, unit length scale. Whenever we talk about VIF, we usually talk about this unit length scale variables. Okay? So, so for multicollinearity, that is my simple introduction. So what are the few facts to remember concerning multicollinearity? Number one, multicollinearity means dependency among regressor variables. If I ask you for a definition, that's how you can write it. Number two, what is so bad with multicollinearity? Well, it inflates the variance of a regression coefficient, or few of them. The higher the dependency among the regressor variable, the more severe this problem is. So why do we care if the variance is high? Variance is high means your estimator is not trustworthy. Yeah, no good. Sometimes it's just useless. Sometimes worse than useless. It leads you to the wrong direction. You're supposed to sell share today, to maximize your profit. Instead, you buy some more. Then you end up losing money. So that's not good. So how do we measure, how do we detect multicollinearity in a data set? Calculate VIF. If it is 2.5, more than 2.5, then we have some evidence. The higher the number, the higher the evidence. So for uniformity, maybe I will just choose 2.5. I have no preference actually, because all these are subjective. But some students are very nervous. Can you tell me which one to use? I cannot. Well, I tell you my choice, so that you don't bug me anymore. I will choose 2.5, okay? If it's more than 2.5, there is multicollinearity. I forgot what I used in the tutorial. So if I use 5, then I lie, okay? Alright. Don't worry, it's just subjective. So the next topic that I want to talk about is, why do regression coefficients have the wrong sign? Well, there are 4 reasons here. One, the range of some of the regressors is too small. You didn't collect enough data. Like the age of, I have this data set ER2103. The age is just what? Maybe 19 to 22. The range is very small. I should expand it a bit more. Important regressors have not been included in the model. Multicollinearity is present. Multicollinearity also causes problems. Well, we'll see how. Computational errors have been made. You make big blunders. That one I will not explain, because it's just computational errors. You make some errors. Maybe you didn't enter the data correctly or some reason. Alright, so reason number 1. Let's just look at simple linear regression, where the variance, let's look at variance of beta 1. There should be a head here, because This is an estimator. Beta 1 is a constant, there's no variance. So variance of beta 1 hat is sigma squared over SXX. That's what we learned in simple linear regression. Now take a look, closer look at this formula. Look at the denominator. Here. That's SXX. The denominator says what? It's the, I think I missed out another one, square. Is that another 2? I'll make the correction later. So it's the sum of square of the deviation of xi from the mean, sample mean. And so that's the variance. So what happened here is, if you have, let's say, 3 numbers very close together, and then somewhere is your sample mean, and so this is your range of your x. Yeah. So, so if you have a very small range of x, then you can see that this sum of square of deviation will be small. And when it is small, the variance will be large. The denominator is small, then this will be large. Now, what if I collect my x over a wider range? Here's my sample mean somewhere. Here's my range of x now. In this case, you know, the denominator is a measure of the spread of the x values. So for this case, I have a bigger spread. I have a big spread. That means the denominator is large, and so the variance is small. Okay? So, now let's look at this graph, which I got it from the textbook. It's a beautiful graph. I don't think I want to draw it on my own. I'd rather watch TikTok instead of redrawing this. Yeah? So you are very particular whether I took it from the textbook or not. Yeah, I don't know why. What's wrong? It's a beautiful figure. Now let's look at the sampling distribution of beta 1 hat. So this is beta 1 hat. The true value is here, is positive. And this is the PDF of beta 1 hat. This is a PDF. And the variance is equal to this. So suppose this variance is very large. Then what happened? Then what happened is this. What it means is this. If you take a sample, you do a regression, the chance of getting a beta 1 hat that is negative is this one. Here's the probability. Can you see how big this probability is? Well, it's less than half, but it's quite substantial. It can happen. So what that means is, it should be positive. But because your spread here is small, variance is large, so it's likely for you to get a negative beta 1 hat. So that's the reason why small range of the regressive variable could lead to an incorrect sign of your regression coefficient. Okay? I hope that is clear. Now, second one is a little bit more abstract, but I think I can explain it until you understand it. So here, why is it that some of the signs are incorrect? All right. So tell me, I have fitted two models. One is x1 alone, one is x1 and x2. Now compare this one and this one. Compare them. The regression coefficient for x1 is 0.463 if we ignore x2. The regression coefficient for x1 is minus 1.222 if we include x2. So what is the definition of partial regression coefficient? This means if I fix this, if I fix x2, for every unit increase in x1, I expect 1.222 units drop in the response. Alright? Here, for every unit increase in x1, I expect 0.463 units increase in y. So which is correct? Obviously, one of the signs is not correct. Yeah? So which is the correct one? So let's look at the diagram. So in the diagram, again I got this beautiful graph from the textbook. Save me some time for my TikTok hour. Yeah? So y here, response, x1 here. So ignore x2, there's no x2. First model, we don't consider x2. We look at the points here, just the point here. So what do you see? Well, if you can't see it, let me just draw, just draw the outline of the distribution of the points. Can you see that there is a positive relationship between y and x1? Yes, there is. That's why when you do a regression on y on x1, you are going to get a positive slope. Okay? But this is because you ignore an important regressor variable called x2. Now, these 2 points are based on x2 equal to 2, x2 equal to 2. These 3 points, as you can see from the data, are based on x2 equal to 4. These 2 points are based on x2 equal to 6. Correct? So, what happened here is, if you fix x2, suppose x2 is 2, what is the relationship between y and x1? If x2 is fixed at x2, and if x2 is fixed at 2, what's the relationship between y and x1? This one. So there's a negative relationship. If you fix x2 at 4 and you regress it, it's negative. If you fix x2 at 6, the relationship between y and x1 is also negative. That's why when you include x2 into the picture, you now have a negative relationship. So the relationship is actually negative for a fixed x2. So, which one is correct? Of course, this one. There's an important regressor variable you should not omit. Alright, part 3. Multicollinearity is present. Okay, well, I hope by now you know what is multi-collinearity. It means high dependency between two variables. So here, I have a data set that I created, y here, and two regressor variables. Now let's just look at the scatter matrix plot to see how highly correlated they are. This is x1, this is x2. So you can see that they almost, the correlation is almost 1. Correlation coefficient, highly correlated. That means if you increase, that means you should, when you do a regression for y against x1 and x2, you should expect the same regression coefficient for both, right? After all, hey, they are almost identical. So let's do a regression. Let's just do it on, let's say, try x1. And, well, the regression coefficient is positive, which is not surprising. See, it's positive. Y versus x1, positive. So that's true. So this regression coefficient is correct. Yeah? So let's do another one. Y against x2. So let's take a look first. So this is this x2. See, y against x2. You should also expect to have a positive regression coefficient. Yeah? Do we get it? Yeah, it is. Y against x2. Yeah, correct, son. Let's do it together. Let's do it together. Well, then now we got this. One negative, one positive. Why? Multicollinearity. Multicollinearity mess up your sign. So, multicollinearity is another reason why the sign could be wrong. It should be positive for both. Alright. So let me just do a review first before I continue. So why do regression coefficient have the wrong sign? Number one, the range of the regressor is too small, so the spread, the variance of the estimator of regression coefficient is very large, so you might get a negative value. Number two, some important regressor variables have not been considered. If you consider it, like the example that I show you, x1 will have a negative slope, which should be the case, because that measures the increase in y for every unit increase in x1 for a fixed x2. Third reason, multicollinearity. So multicollinearity is really what I call the curse, C-U-R-S-E, the curse of regression. If you don't deal with it, your model can be useless. You will lose your shirt when you try to invest in the stock market because you have not handled multicollinearity well. Alright? The fourth reason, errors in computation, errors in data entry, and so on. So the first thing to do is to check your data carefully. Now, next is, I want to talk about X matrix with orthogonal columns. This topic is of great importance when we talk about experimental design. Maybe I will take a break right now. I think it's a good time to take a break. and then 5 minutes. We'll continue with this one.
There's no question.
Let's continue. All right. So next is I'm going to give you a small review of certain things you learn in linear algebra, which will be useful for us here. Number one is independent vectors. I don't know whether you learn in matrix or what, or vector algebra, you know. We only need some very simple concepts. Number one, two vectors, let's say non-zero vectors, and C1 and C2 are two scalar constants. We define the two vectors to be independent if C1 times vector u plus C2 times vector v is 0, then C1 and C2 must be 0. Actually, if you take a look carefully, it simply means this. Two vectors are independent if you cannot write u as a function of v. That's what it means. If you can derive u from v, then u and v are dependent. So you can also apply this to this idea of independence to two or more vectors. So if none of them can be written as a linear combination of the others, then they are called linearly independent. So I will give you an example, a few examples here, help you to understand. Let's just say I have this vector 1, 0, 0. Now v is 0 to, let me just make it simpler. Let's say 3, 0, 0. Are these two vectors independent? Well, independent means what? If you apply this definition, so C times U, maybe I'll just write it, C times 1, 0, 0, C1 plus C2, 3, 0, 0, equal to 0, 0, 0. Can I have, does it imply C1 and C2 equal to 0? Not really, right? I can choose, let's say C1 equal to 3, C2 equal to minus 1, then I will have the 0, 0, 0 vector. So, see, I don't need to have this. That means these two vectors are not independent. Okay? They are not independent. Okay, let's try another one. Let's try 0, 3, 0. 0, 3, 0. So 0, 3, 0. Are these two vectors independent? So what are the choices of C1 and C2 for this to be zero vector? Well, we want this to be zero. See, independent means if you look at any linear combination, if it gives you a zero vector, then this two must be zero, which means U cannot be written as a function of V. So, what choice do you have for C1, C2 here? There's no other choice. It's obvious. C1, this implies C1 must be C2 equal to 0. So they are independent. Okay, see that? So, if you can express one as a function of the others, then it's called dependent. So let's say, let's look at three vectors. U, V, W, let's say. 2, 5, 0. Are these three vectors linearly independent? So I'm talking about more than two vectors now. Are they linearly independent? So you can try this. 1, 0, 0 plus C2, 0, 3, 0 plus C3, 2, 5, 0. We already know that V and U are linearly independent, but are these three linearly independent or not? So C3 equal to 0. Can I get all the C to be 0? Well, not true, right? You can choose, for example, C1 to be 2. I can choose C1 to be, okay, if I choose C1 to be -1, then I will get a 0 on top. How about C2? C2 and C5. How do I get a 0? I think that is easy. I can, how about if I choose 5 here? I choose C3 to be -3. Then I also get, not 0, 0 vector. So how do I get a 0 vector? You can see that this, if I choose C2 to be 5, C3 to be -3, I get 0. Am I right? So what that means is this vector can be obtained as a linear combination of these two. You can get it. Do I need anything else? No, I think I need more. Maybe -2? I should use -2. Let me check one more time. Okay, C1 is -2. You didn't say anything. So, here's an example where the three vectors are not linearly independent. You can have two of them independent, but three together, they are not. Because you can actually get this one from linear combination of these two. Okay, you can choose some C1 and C2 to get that. For example, multiplies U by 2, multiply this by 5/3, you will get this vector. So if you can get one vector as a function of the other two, then they are not linearly independent. Okay, very simple. Next is orthogonal vectors. Orthogonal it's a very simple definition. It means the dot product is 0. It means dot product is 0. So what is a dot product? It's just U transpose times V. So this, let me write it down. This is U1, U2, up to UK, multiplied by V1, V2, up to Vk. So this is just U1, V1, plus all the way up to UK, Vk. So if the dot product is 0, then they are orthogonal. Okay? Now, there is one more fact I forgot to state it here. I don't know what happened to the 3. Maybe it's here. Orthogonal vectors, vectors imply independent vectors. So orthogonal, if you have two vectors that are orthogonal, then that means the two vectors are independent. You got that? So let's look at one example. So let's say U is 2, 3. V is 1 minus 1. These two vectors orthogonal. Okay? U transpose times V is 2 times 1 plus 3 times minus 1. So that is equal to, so this times this, okay? So that is 2 minus 3 equal to minus 1, not 0. So they are not orthogonal. You know how to check? Okay? So that's orthogonal. How about this one? U equal to 1, 0. V equal to 0, 1. So U transpose V is 1, 0 times 0, 1, which is 1 times 0, 0 times 1, 0. So this is orthogonal. You got it? Remember, you'll come in handy later when my alarm sounds. Okay? So, now let's look at a cookie example. You know, so far if you collect data, these regressor variables are going to take on any value. It's not going to be easy to have orthogonal regressor variables. These orthogonal regressor variables come from design. So suppose I want to bake some cookies. Yeah, you know, making cookies is very simple. I've done it before. Yeah, and my kids love my cookies. After I make them, they all come and eat. Why? Because I use what I learned in statistics to get the best cookie. Yeah, that's true. That's the power of experimental design. How? Well, I start from 0. I don't know anything about making cookie. I only buy Famous Amos. But after I look at it, it's so simple. I can do Famous Gun, you know, and my own cookie. All I have to do is make sure 3 factors are taken care of. And what are they? Oven temperature. Time for baking the cookies. How long? Too long, become charcoal. Too short, not cooked enough. Temperature. Too long, too high, also charcoal. Thickness. Do you want it crunchy? Do you want it crispy or whatever? Yeah. So these are three important factors. So I can set this. Suppose I don't know what temperature to set in the oven. Of course, I can look up at YouTube, get some idea. But every oven is different. So I set for factor X1 temperature. I choose one temperature here, one temperature. So for time to cook, I can try 10 minutes or 15 minutes. For thickness, I can try half a cm or 1 cm. So I can choose. And then so for each factor, I have two levels. And I can actually design an experiment to do this. In other words, I have 2 times 2 times 2 settings, 8 settings. I need to make 8 batches of cookies. Each batch will correspond to each setting of a temperature, time, and thickness. 2 times 2 times 2. And so this figure, a point here shows what type of setting. So for example, it means factor X2 high, and factor X3 high, and so on. So this is low. Let me see. So for example, this one means factor X1 high, factor X2 is low, factor X3 is low. So this 8 settings can be represented by the 8 points of the cube here. Just a way to visualize these 8 settings, nothing different. And for a low setting, I define to be -1. High setting is +1. So now I will then make the 8 batches of cookies, and my regressor variables will be the 8 setting. So Y1 refers to the 8 settings, okay? 1, 2, 3, 4, 5, 6, 7, 8. So this is all the high setting. So this one has some high and low, and so on. So this is an example where I have orthogonal regressor variables. And because if you multiply any two columns, the dot product is 0. They are orthogonal. Any two columns orthogonal. So by design, it is possible. So let's just study this matrix X with orthogonal columns, see what happens. So let's say we have a full model, X1 beta 1 plus X2 beta 2. And all the columns are orthogonal, let's just say. Let's consider 2 reduced models, X1 beta 1 and X2 beta 2. So now, here, I want to find out what is the relationship among these 3 regression sum of square. So for the full model, it's very simple. I have my x is just x1 and x2. So when I multiply out, it looks something like this. And then I have beta 1 hat, beta 2 hat, and so on. Now because the columns are orthogonal, this part of the matrix will be 0. This is also 0 because they are orthogonal. And so this is 0. So this is a 0 matrix here. This is 0 matrix. But this part is not 0. This part is not 0. And you can then multiply this, you expand this, you will get two equations, you know, because 0 you don't have to consider. And then beta 1 hat can be obtained by this, beta 2 can be obtained by this. So now, what is SSR beta for the full model? SSR beta for the full model is beta hat prime x prime y. And so this is the definition, nothing new here. So I just write in terms of beta 1 and beta 2, x1 and x2. So that's what it is. So that's nothing new. This is what we know. So now, so what happened here is, what is SSR beta 1 for the reduced model? For the reduced model, there are two reduced models that we are considering. One of them is this, and another one is this. So, for the reduced model involving x1, the sum of square of regression is this. For the reduced model involving beta 2, x2, that is the sum of square. So, you can now see a relationship between the sum of square regression to these two. It's just the sum of it. It's just the sum. Yeah? So sum of square regression for beta is this two. So that's one important consequence of the fact that all the x1 and x2 are orthogonal. Now let's look at this. This is more interesting. This is the regression sum of square of beta 1 after we've accounted for beta 2, x2. So according to the definition of this, is the sum of square regression for the full model minus away this. So this is definition. But what is SSR beta? SSR beta is the sum of the two. So this sum minus this, you get SSR beta 1. So SSR beta 1, given that you have accounted for beta 2, is just SSR beta 1 without having to consider beta 2. Why? Because the regressor's x1 is independent of the regressor x2. That's why. It's like conditional probability that you learn in the module, probability, right? See, if x1 and x2 are independent, then the sum of square regression for beta 1 after accounting for beta 2 is exactly the same as regression sum square for beta 1 without having to consider x2. Why? Because x1 and x2 are independent. Orthogonal means independent. So same thing for the other one. So for the cookie example, I make 8 batches, and here's my design. So for each 1, 2, 3, 4, 5, 6, 7, 8. So for each time I make it, I decide, what are the settings that I need to use. So this is the setting that I'm using. And then I can have x1 here. Suppose I define my x1 here, and then x2 to be the other part. So this is, let's say I define this to be x1 and then x2. I think I have to move it away. Give me a minute. I'm going to move it away. Okay. So in this case, you can check. You can check easily that this is in fact true. Now, this matrices with orthogonal columns are important in design experiment. You will learn much more in this course. And this course is a very useful course, and I encourage all of you to take it. Yeah. Okay. So, is there anything else? I think that's the end. Okay, I think I skipped one part, critical part. Let me just go back there and just mention it. So, for the cookie example, actually I only have 3 regressor variables. Yeah, but for this model, I've considered the interaction of all of them. x1 times x2 means you multiply this. So minus 1 become plus 1. Plus minus 1 become minus 1. That's how I get the column x1 and x2. And I is just a column of 1. So when I analyze this, I will be able to find out whether which of the regressor variable x1, x2, x3 is significant. But in this example, actually we are not so keen to find out which is significant. We are more interested, at this each setting. At each setting, you either choose a high or low level of a particular factor. So for example, this point here, I have factor 3 at high level, factor 1 at low level, and then factor 2 also at low level for this particular point here. So after I make these 8 batches of cookies, and then I let my kids try every one, and then they'll tell me this one is the best. They will all turn out different, but if they tell me this is the best, then I know next time when I make my cookies, I should choose high level of factor 1 and high level of factor x3 and low level of factor x2. And what does that mean? So I can go back to this, high means 1. So after that, I would have mastered my skill, I know I need this temperature, this time, this thickness, and then that will be the best cookie. All the other setting, maybe not that good. Alright? So that is the idea of experimental design. And that is when this orthogonal regressor variable comes in. As you know, quiz today is probably the last 5 minutes because my alarm has not sounded. So let me just review until my alarm sounds. So what have you learned today? Well, we learn multicollinearity. Multicollinearity is simply dependency among regressive variables. So what's so bad with multicollinearity? Because the presence of multicollinearity will inflate the variance of your regression coefficient and make them not trustworthy. And then the second topic is, why do regressions have the wrong sign? Well, if you have a regressor that has limited range, you will end up having a large variance. That means the probability of getting an estimate of a regression coefficient to be negative will be high. Or you have, what's the other reason? Well, you have not considered all the important regressors. That's why you got the wrong sign. And then thirdly, multicollinearity also can give you the wrong sign. And the fourth reason is just blunders. Yeah. Finally, we talk about orthogonal. So two vectors are orthogonal if the dot product is 0. And two vectors are independent if C1u plus C2u are V. Two vectors are independent. That means you must have C1 equal to C2 equal to 0. That's called independence. Why? Because you cannot express one vector as the other. So that is independent. So this is orthogonal. Now, I'm actually just touching on the surface of orthogonal regressive variables. So I'm not just an introduction, but nothing much. Okay? So let's just wait for the quiz to show up. I think I will activate it now. It's coming very soon. I will turn it on. It's on now. But the quiz won't start until 11:30, so let's just wait. Let's just wait a while.
Please.
By the way, if you want to know about midterm exam, I'm not going to say anything, but you can find everything in chapter 1. So it's based on all the topics we have learned in the first half of the semester until now. If a tutorial contains topics that I have taught here, whether I teach it or not, it still will be tested because it's based on chapter 2 and 3. Alright? Okay, I think time's up. Let's do the quiz. Should be simple.
Why can't you just show us the quiz like beforehand? Why is this like okay, multiply them. 2, yes, they are. This top product that goes on 3 minutes long. No, actually, I'm not using this lecture thing right.
Another announcement, next week I'll be traveling out of Singapore for a week in China somewhere. So I